years ago, this is the sort of thing that happened quite often, especially when some oil seeker happened to stumble upon a new pool. Now, such occurrences were very dramatic, but unfortunately, many millions of barrels of oil were lost, never to again be recovered. Now, today, such occurrences are not very common because drilling for oil has become a highly scientific operation. And to tell us of the modern techniques in this field, both in the matter of discovering oil deposits as well as bringing the oil to the surface, we have invited as our special guest on Science in Action, Mr. Howard G. Vesper, Vice President of the Standard Oil Company of California. Welcome once again to Science in Action, Mr. Vesper.
Thank you, Earl. I'm delighted to be on the show. And I think I heard you mention a moment ago the term oil pool. We might start by just saying that I believe most people have somewhat of a misconception of what an oil pool below ground is. Most people think it's a reservoir or lake of oil, something like this, with rock above and rock below. Well, actually, it's something quite different. We might visualize it by taking this little cylinder of small grains of sand. Imagine that these are cemented together with many pores in between in which the liquid is retained. And we can show how the crude oil is actually kept in the pores of this rock by pouring the liquid in. You notice that it fills the pores very, very easily. This is what the oil man refers to as an oil pool.
Now, according to the best opinion, oil comes from the decomposition of very small organisms, both plants and animals. Most of these are too small to see, but if we put them on a slide and place them under the microscope, we find that there are all sorts of beautiful forms, especially in these diatoms which we see.
All of these plants and animals decayed to make chemical substances and finally to make oil, which is accumulated at the bottom of the oceans and trapped by layers of sand and mud. Gradually, over the geologic times, the sand would harden into a rock which we call sandstone, which looks something like this. And the mud overlaying the sand would finally harden into a rock known as shale, which looks like this.
Well, now, if we were to make a very thin section of this sandstone and place it again on our slide and put it into a projector, we would find that there were many spaces and pores and different sorts of holes connecting the various areas in that.
Those are very important, Earl, because those are the holes about the diameter of a human hair through which the fluids flow. And as a result, we call this sort of rock, this sandstone, a permeable rock.
Now, by contrast with that, the shale, if we were to make a section of that, a very thin section, and examine it either under the projector or the microscope, we would find that the holes, the pores were so small that fluid couldn't go through it.
That's right, and for that reason we call this kind of a rock impermeable. Now, Earl, during the thousands of centuries that these rocks were being formed, salt water and oil were forced into the pores of the sandstone and gradually accumulated in this rock. We can illustrate that by using a common sponge, which has soaked up here a lot of water. And as the oil and the rock are being soaked up, I think you can imagine that the oil, being lighter, would tend to travel toward the top of the sandstone or the sponge.
Well, coming back to our sandstone core here again, the oil would come up here and then it would run into the shale, couldn't get through that, and then we would have it trapped at this point.
That's right, and we can illustrate that perhaps by using a little sponge rubber model. If this were a cross-section of the Earth's surface, the black part might represent the shale or the impermeable rock, and the section with the diagonal lines would be the sandstone impregnated with oil. Now, over the geologic centuries, the Earth's surface might tend to buckle, something like this. And if this were to happen, I think you can see that the oil would tend to migrate up in here from both sides, would be held in by the impermeable shale on the top and by salt water on both sides here, and we would have an oil trap. This is what the geologist calls an anticline.
Now, in addition to these anticlines, you have such things as faults and pinch-outs, both which hold the oil in addition to the anticline.
Yes, we do.
But the big problem is still how to locate the oil that's trapped down there hundreds of thousands of feet below the surface. Now, one of the ways that this might have been done in the early days was by means of doodlebugs or perhaps even divining rods. Now, according to the best technique, a divining rod is held balanced in about this position. Person walks around, and then at the proper point, the rod starts to dip. I guess we should drill for oil here, right, Howard?
Well, I wish it were that simple, Earl, and we'd certainly like to find oil in San Francisco.
Well, actually, in your work, you use a variety of scientists, such as geologists, physicists, mathematicians, chemists, and many others to determine just where you're going to drill.
Earl, finding oil these days is a very highly scientific sort of a thing, and we use all of these people that you mentioned. We generally start with a geologist. And if you can imagine this as representing a terrain which we think has some oil possibilities, the geologist would be the first one to examine it. He'd look at it with relation to known geologic structures, places where we'd already found oil or knew oil to exist, and he would determine that it was a likely spot. And then when he had determined that, he'd call for the help of the geophysicist and, in turn, the seismic crew who would explore a ridge like this, for example, with the seismograph.
Now, this is your crew out in the field?
That's right. And you'll see them. They actually put a small charge of dynamite down a little hole and create a very miniature, localized sort of an earthquake. There it goes. And that sets sound waves to going off that go down below the ground and are recorded on something that we call a seismogram that looks like this.
And this seismogram, of course, now, if I understand this properly, your instrument is set up here and your charge is also set off at this point.
Yes.
And this is a time interval. Now, up to here would be about 1 second. Now, I notice that there are some different types of marks through here. What do those indicate?
Well, these are the record of the reflections of the sound waves that have been set off at the surface of the Earth, gone down a certain number of hundreds or thousands of feet, and encountered different sorts of rock formations and been reflected back to the surface and thus measured as these wavy lines. You see, Earl, you can explain this principle, I think, very simply if you just imagine that you and I were standing on the edge of a canyon. And suppose we wanted to find out how far it is across to the other side of the canyon. We would shout, perhaps, and we'd measure the exact length of time it took our voice to travel from one side to the other. Now, we know that sound travels about 1,100 feet a second in air, and so by measuring the time it takes our voice to return, we'd know just how wide the sandstone is, or the canyon is. And it's the same principle exactly that we use in the seismograph in measuring subsurface formations.
In other words, the rate with which the shock waves go through the various types of material in the earth determines what sort of material you have there.
That's right. For example, sandstone, we know that sound travels at the rate of about 8,000 feet a second. And other rocks likewise have different rates of transmission. And so knowing that, as we come back to our seismogram here, we can interpret this by seeing that these various sections where there are unusual reflections of sound from these rock formations deep in the earth mean a special sort of a rock formation. And this aids the geologist to tell whether or not this is a likely region in which to find oil.
Well, despite the fact that this seismograph is the best way you have so far of determining where oil is, still you can't be absolutely sure that it's there until you have put down a test hole to make certain.
Well, it's an old saying in the oil business, Earl, that oil is where you find it, and you certainly are right. We have to drill in order to do that.
Now, on this model derrick, how would you go about that?
This little model, incidentally, was made by one of our young producing people in our Standard Oil Company of California producing department, Mr. Don Rinkin. I think it's a very nice model. The derrick up here, I think, is familiar to most people who've been out in the oil fields, and it's used to raise and lower the drill pipe on this block, which goes up and down in the derrick. Actually, the drill pipe we use weighs about 25 pounds a foot, and it's about 4.5 inches in diameter.
Well, now, in other words, you attach the pipe one on the other, and they keep going down continuously into the ground.
That's right, Earl. Each section of drill pipe is about 30 feet long, and we screw these together, and since some of these oil wells go down as much as 20,000 feet, you can see that there are hundreds of sections of drill pipe screwed together. Now, down at the bottom, in order to do the real work, we have a bit which actually chews away at the rock and cuts away and actually makes the hole.
I was surprised in finding out that this diamond bit has a value of some $4,000.
It doesn't look like it, does it? But that's right. This is worth about $4,000, and I think you can see why if we look at it carefully here, because these little individual chips all around the face are real diamonds. They're very hard. This is a special kind of a bit that we call a core bit, and it's used to rotate and cut away a section of the rock through which we're drilling. The section might look like this. This happens to be a core sample of a shale. This is brought to the surface and again used by the geologist to determine the kind of formation in which we're drilling.
Well, now this bit is of another type. This is the one you commonly use.
This is the more common type. This actually rotates. It's screwed onto the drill pipe and rotates thus. It's a wicked sort of looking thing when you look at it closely. And these teeth, very hard alloy steel, are what actually cut away the chips of rock.
Where does Mr. Kelly come into this?
Kelly's another famous oil field name, and what actually happens is that this bit is attached to the bottom of the drill pipe, and the drill pipe is screwed together for some thousands of feet. And if we can go back to our derrick here, it comes up through a rotating table in the derrick floor and attaches onto a square pipe that's called the Kelly. And so when you drill, you have a whole sequence of things happening. You have the drill table turning the Kelly, and the Kelly turning the drill pipe down below ground, the drill pipe turning the bit, and the bit cutting away the rock. I know that sounds a little bit like a lyric from this song, Old MacDonald Had a Farm, but that's the way it works.
It certainly does. Well, now, I have a question on these types of shafts that you make in your drilling. On this model, I can well understand this type of a shaft, but this one over here, with all of these contours on the side, looks a little bit different. Why all the bulges?
Well, Earl, imagine that this is a cutaway section down some thousands of feet below the ground. The shaft on the right is the kind we'd like to drill. In the center, you'll see these 30-foot sections of drill pipe represented here, tied together. Now, in order to drill a straight hole, this should be in tension. There should be a pull on both ends. And if I start this drill pipe to moving, you'll notice that the one on the right moves very smoothly because it is in tension. The one on the left, because it's not properly in tension, is loose and acts like sort of a corkscrew. And the net result is that we get a very irregular hole with these bulges, a very inefficient kind of a hole.
Now, way down at the bottom, of course, is this drilling bit, some of which we just examined. But what about the chips that are left in there? Do they stay there, or do you take them out?
That involves something we didn't mention earlier, and that's a drilling mud. Now, there's a very special kind of a mud made when we're drilling these wells. It's on the surface of the derrick. There's a mud tank and mud pumps. And it's actually pumped down from the surface of the ground through the middle of this drill pipe, right down to the bottom of the hole, and comes out of the bit. And just where you're pointing over there are the eyes in the bit where the mud comes out. And it picks up then the rock chips, the cuttings, and brings them back up around the outside of the drill pipe to the surface where they can be removed. And they look something like this when we recover these rock chips. These, of course, are also very interesting to the geologist because they're another indication of the kind of rock through which we're drilling.
Very nice, but one of the most interesting things that you've turned up that to the marine biologist would be this sort of a core with clams in it. Clams that resemble forms that live today along the Pacific coast.
Well, I can see why, because of your marine background, you're interested in this, Earl. And you're quite right. The geologist always looks at these cores for marine fossils or evidences of marine life, because he knows the kind of marine life that is most apt to be associated with oil. And so by